They scraped them off dinner plates, they swept them out of seafood restaurants, they loaded them onto trucks, drove them to the coast, dropped them onto barges, and poured them into the Gulf of Mexico. 500,000 tons of discarded oyster shells. Waste. Garbage. And what came back from the bottom of that Gulf will make you rethink everything you believe about how nature works. Because here's the thing. The people who did this did not expect it to work. The scientists running the program quietly braced for failure. Environmental groups called it ocean dumping, dressed up as conservation. Fishermen who had worked those waters for generations showed up to public hearings and said this would finish off whatever was left. Loud, credible, experienced people looked at the plan and saw a disaster. They were all wrong. And the way they were wrong is one of the most remarkable stories in the history of modern ecology. Because what grew on that Gulf seafloor did not just exceed expectations. It rewrote them. It broke every timeline, every projection, every assumption about what is possible when you give a broken ocean system a single missing ingredient. And the outcome is still unfolding right now. This is that story. To understand what happened at Cedar Key, you first have to understand what was lost. And to understand what was lost, you have to go back several centuries. Before the restaurants, and the processing plants, and the pollution, and the coastal development that changed Florida's Gulf Coast permanently. The eastern Gulf of Mexico was once one of the most productive oyster ecosystems on the planet. Oyster reefs stretched across hundreds of square miles of shallow coastal water. Not scattered patches, dense interconnected networks of living structure that had been building themselves for thousands of years. Each generation of oysters grew on top of the dead shells of the generation before it. Layer by layer, century by century, the reefs climbed higher, spread wider, and became more complex. They were not just a shellfish habitat, they were the foundation of the entire coastal ecosystem. Roughly 300 species of marine life depended on them. Fish, crabs, shrimp, sea turtles, wading birds, the whole food web, built on top of an architecture made of shells. Then came the industrial harvest, the coastal development, the runoff from agriculture, and the pollution. Over the course of about a century, the reefs were hollowed out, dredged up for construction material, buried under sediment from altered waterways, poisoned by nutrient overload. The network that once stretched for hundreds of square miles contracted, degraded, and in most areas simply collapsed. By the early 2000s, the Gulf floor near Cedar Key was essentially flat, soft, sandy bottom, almost nothing attached to it, almost nothing living on it. And here is the brutal ecological trap that made natural recovery impossible. Oyster larvae need a hard surface to settle on. They drift with the current in the water column for a brief window, searching for somewhere to attach. In a healthy reef, that surface is the packed, layered shells of previous generations. But when the reefs are gone, the larvae drift and die because soft sand gives them nothing. No settlement means no new oysters. No new oysters means no new shells. No new shells means the next generation of larvae also drifts and dies. The cycle had snapped and the Gulf had no mechanism to restart it. The Florida Fish and Wildlife Conservation Commission was staring at a self-reinforcing collapse with no obvious exit. And that is where the shells came in. Between 2007 and 2024, the Commission ran a program that seems almost too simple to be serious when you first hear about it. They partnered with restaurants and seafood processors across Florida to collect discarded oyster shells, the ones normally trucked to landfills, cured them to reduce bacteria, loaded them onto barges, and deposited them on the sandy Gulf floor near Cedar Key. More than 500,000 tons of them over 17 years. The critics who showed up to oppose the program were not cranks. Their concerns were scientifically grounded. Piling 500,000 tons of shell material onto a soft-bottomed ecosystem could alter currents, smother what little life still clung to the sand, and disrupt the fishing grounds that a generation of Gulf Coast families depended on. The fishermen who had read those waters for decades had every reason to be skeptical. The Commission's argument was blunt. These shells were going to landfills either way. The worst case was you moved some waste from a landfill to the seafloor. The best case was you handed the Gulf the one thing it could not produce for itself, a hard surface for life to grab hold of. The gamble was worth taking. What nobody fully anticipated was how fast the gamble would pay off. The first monitoring teams returned to the deposit sites 18 months after the initial shells went in. They came prepared for the obvious outcome. Silt-covered mounds, a handful of opportunistic organisms at the edges, a long wait before anything resembling a reef appeared. That was the normal pace of artificial reef development. Years, sometimes many years. And these were not engineered concrete modules or purpose-built reef structures. They were restaurant scraps. What the teams found instead stopped the scientists cold. Life was colonizing the shells, not on the multi-year timeline they had prepared for, but in months. Marine organisms were attaching and establishing at rates that had no precedent in the scientific record for any comparable effort. The shells were not sitting on the seafloor as inert calcium mounds. They were behaving as biological triggers. And to understand why, you had to look at something too small to see with the naked eye. The first colonizers were not fish. They were not even oysters. They were bacteria. Within days of the shells settling on the seafloor, microscopic bacteria began spreading across the calcium carbonate surfaces, forming biofilms, thin, organized layers of living chemistry that converted dead shell surface into functioning microhabitat. This was not random. It was structured biological groundwork, and it happened fast, because the shells were not chemically passive. Oyster shells are composed largely of aragonite, a form of calcium carbonate that slowly dissolves in seawater. As the shells released calcium ions, they generated small alkaline pockets in the water immediately surrounding them, localized chemical shifts that created exactly the conditions calcifying organisms need: barnacles, tube worms, young oysters. The creatures that build reefs are the ones that need calcium-rich, slightly alkaline water to construct their shells, and the shells on the seafloor were manufacturing those conditions automatically. This distinction matters enormously, and it is easy to slide past. A concrete block or a sunken steel hull provides a surface. It does nothing to the water chemistry around it. An oyster shell provides a surface and actively alters the local chemistry to invite colonization. The substrate was recruiting its own colonists. It was not waiting to be discovered. It was advertising. Weeks after the bacteria established their biofilms, diatoms and microalgae moved in, building the base of a food web. Tiny crustaceans and larval mollusks arrived to graze the algae. Those grazers drew juvenile fish. Each stage of life created the conditions for the next stage, a self-reinforcing biological ladder assembling itself in the dark at the bottom of the Gulf, built out of what had been sitting behind restaurants, waiting for a landfill pickup. By the end of the first 6 months, water samples and sediment cores showed a complete microscopic ecosystem had established across the shell surfaces. From the surface of the water, the deposits looked like nothing, lumps on the seafloor, unchanged, unremarkable. But the data told a completely different story. The invisible phase of reef development, which typically takes years on conventional artificial structures, had compressed into weeks. The scaffolding was already in place. Everything visible that came afterward rested on this foundation nobody could see. Once the microscopic layer was established, the process that the Commission had actually designed for could begin: oyster recruitment. Oyster larvae float in the water column during a narrow developmental window. They have a limited time to find a hard surface, settle, and cement themselves to it before they die. In a healthy reef ecosystem, this has never been a problem. The existing reef is everywhere. The larvae find it quickly. But in the degraded Gulf, they had been drifting through open water with nowhere to land. The deposited shell mounds changed that immediately. Each pile was a concentrated landing zone placed directly in the path of Gulf currents that carried drifting larvae. Suddenly, the spat that had been dying by the millions in open water had somewhere to go. University of Florida. Marine lab researcher Dr. Bill Pine, who had been among the scientists monitoring the Cedar Key sites, recorded juvenile oysters fastening to the deposited shells in numbers that blew past every projection. The larvae were finding surface, settling, and beginning to grow at a pace that the program's models had not predicted. Within the first year, the broken reproductive cycle had its starting point back. By the second year, those juveniles had grown into reproductive adults. They began releasing larvae of their own. Those larvae settled on the existing reef and built a second generation on top of the first. This is the moment the project crossed a threshold that conservation biologists rarely witness. It stopped being a human intervention and became a natural process. Nobody added another shell. The oysters were doing the work entirely on their own. By year 3, survey data was recording an average of 847 oysters per cubic meter of deposited shell. Adjacent soft bottom areas with no substrate, essentially zero. Same water, same currents, same larvae drifting overhead. The only variable was the presence of a hard surface, and the difference in outcome was total. And the reefs were not staying put. Oysters were dying and leaving their shells behind, which created substrate for the next wave of settlement, which added more height and area, which attracted more larvae. The reef was building itself horizontally and vertically, exactly the mechanism by which natural reefs had grown before the natural ones were destroyed. Among the most vocal opponents of the shell program from the beginning was charter fishing captain Mike Lent. He had testified against it at public hearings. He had warned the Commission that the project would ruin fishing grounds his family had worked for 3 generations. He was not a casual critic. He was a man with decades of direct experience reading those specific waters, and his professional instincts told him this was a mistake. In 2013, standing at the rail of his boat above one of the established reef sites, Lent watched a thick school of redfish holding in the current around a shell mound. He said something he had never planned to say. "I was wrong. I've never seen fish stack up like that in 25 years in this water." That reversal was not just personal. It marked the moment the scientific data and the lived experience of Gulf Coast fishermen finally told the same story. And what Lent saw with his eyes matched what the survey teams were recording with instruments. Biomass around the reef sites had climbed more than 340% compared with control areas. Species diversity was up 280%. Redfish came first, tucking into the shell structure to feed and hide from predators. Sheepshead arrived next, grazing the invertebrate communities growing across the reef surfaces. Flounder worked the edges where the reef met open sand. Snook appeared in numbers those waters had not seen in years. But the critical scientific finding, the one that separated Cedar Key from every run-of-the-mill artificial reef program, was what Dr. Pine's team found when they dug into what was driving the increase. Artificial reefs made of concrete blocks or sunken ships are well documented for producing a visual spectacle without producing new fish. They concentrate animals that already exist in the surrounding area, shuffling a fixed population to a new address. Drop a wreck and fish will gather at it. That looks dramatic on a survey. It does not mean there are more fish in the ocean. The Cedar Key reefs were producing fish, not just collecting them. Juvenile fish counts, animals born in those waters and surviving to adulthood within that habitat, were the primary engine of the increase. The reefs were creating survival conditions that had not existed before, allowing young animals to live to maturity where before they had no chance. That is the difference between an illusion and a real recovery. Charter operators up and down Cedar Key, who had spent years fighting the program, began formally requesting new reef sites from the same commission they had been opposing 6 years earlier. Hotels, bait shops, and waterfront businesses all reported measurable revenue increases, tied directly to the surge in marine life around the reef sites. What had been sold as conservation had become economics. As the reefs grew, something was changing in the water itself. Something nobody had designed for, something that reached far beyond the reef footprint. A single adult oyster filters between 30 and 50 gallons of seawater every single day. That number is a curiosity when you're talking about one oyster. It becomes something else when you're talking about hundreds of thousands of oysters spread across a growing reef system. The Cedar Key reefs were now processing billions of gallons of Gulf water daily, pulling out suspended particles, excess nutrients, nitrogen, phosphorus, harmful bacteria, and agricultural runoff. With no machinery, no electricity, no staff, no maintenance budget, nature had built a water treatment plant out of discarded restaurant waste, and it operated continuously for free. The Gulf Coast has a chronic and serious nutrient runoff problem. Nitrogen and phosphorus from farms and urban development pour into coastal waters year-round, feeding harmful algal blooms that cloud the water, suffocate marine life, and periodically trigger mass fish kills. These blooms had defined degraded Gulf ecosystems for decades. The oyster reefs were hitting the problem at its source, filtering out the very nutrients that fed the blooms before they could spread. Water clarity around the reef sites began improving measurably within a few years. Dissolved oxygen levels rose, nutrient concentrations fell, and critically, the improvement was not staying contained at the reef. It was spreading outward into surrounding waters, improving conditions across a widening radius from each deposit site. Clearer water lets sunlight penetrate deeper. Seagrass, the critical habitat for juvenile fish, manatees, and sea turtles, needs light to photosynthesize and survive. In murky water, light cannot reach it, and the grass dies back. As the oyster filtration cleared the water column above them, seagrass beds began pushing back into zones that had been too dark for them for years. And here is where the story compounds itself. Seagrass stabilizes sediment, which reduces turbidity further, which lets more light through, which grows more seagrass. A second feedback loop, triggered by the first, sending recovery rippling across the entire coastal system. NOAA research confirms that oyster reef restoration projects generate ecosystem service value projected to reach into the tens of millions of dollars over the life of a program, value that would require extraordinary mechanical infrastructure to replicate artificially. Nature was providing it and improving its own performance every season. The results spread. Alabama launched its own shell recycling program by 2015. Mississippi followed. Louisiana built large-scale reef structures. And in New York Harbor, one of the most polluted urban waterways in North America, the Billion Oyster Project applied the same principle. By December 2025, the project had restored more than 150 million oysters to New York Harbor across 17 acres of reef, recycling over 2 million pounds of restaurant shells to serve as substrate. In 2025 alone, their monitoring teams deployed more than 580 fish and invertebrate traps across 8 reef sites, documenting over 4,000 individual animals representing 44 distinct species, in water that was nearly biologically dead within living memory. The idea was proving durable across radically different environments: warm, shallow Gulf water, cold urban harbor, monsoon coastlines in Bangladesh, where oyster breakwater reefs reduced erosion by more than 50% compared to unprotected control sites. The principle traveled because the biology travels. Wherever you give oysters a hard surface and the right conditions, they rebuild the world around themselves. Then came the test nobody had designed for, the one that changed how coastal engineers talk about oyster reefs. September 2017, Hurricane Irma. Category 4, sustained winds topping 150 miles per hour, catastrophic storm surge. Waves hitting the Gulf Coast with enough force to strip beaches and rearrange shorelines overnight. Irma was not a minor event. It was one of the most powerful Atlantic hurricanes on record, and it made a direct run at exactly the coastline where the Cedar Key reefs had been building for a decade. Nobody had built those reefs as a hurricane defense. That was not in the program design. The goals had been habitat restoration, fishery recovery, water quality improvement. Storm protection was not part of the calculation. But when damage assessment teams worked through the Cedar Key area after Irma passed, they found something that stopped the conversation in its tracks. Shorelines, shielded by the restored oyster reefs, had suffered dramatically less erosion than unprotected stretches nearby. The difference was not marginal. On average, erosion behind the reef sites was cut by 30 to 40% compared with adjacent unprotected shorelines. The visual contrast was visible from a boat. One stretch of coast chewed back, the neighboring stretch largely intact. The mechanism is physical. Waves rolling toward a smooth surface retain their energy and strike the shore at full force. Waves hitting a three-dimensional, jagged, porous structure lose energy to friction. The irregular surface of a living oyster reef, layers of shells, gaps between clusters, overhangs, interlocking surfaces, breaks wave momentum apart before it can translate into erosion. The reef does not just sit in the path of the wave, it disassembles it. Engineers estimated the reefs had prevented approximately $3 million in coastal property damage during Irma alone. The total cost of the entire 17-year restoration program from 2007 to 2024 was approximately $5 million. In a single storm, the program had not been designed to survive. The reefs returned nearly 60% of the program's entire cost in prevented damage, and that was from one event, in one storm season. But the comparison to conventional coastal engineering reveals something even more significant. A seawall is at its best on the day it is installed. From that point forward, it cracks, corrodes, shifts, and weakens. Every piece of hard coastal infrastructure is a system in decline from the moment it is built. Maintenance is constant. Failure is inevitable. A living oyster reef works the opposite way. Storm damage exposes fresh shell surface and triggers new larval settlement. Disturbance stimulates growth. Every generation that survives a storm adds structural height and complexity for the next. A high-density oyster configuration has been measured in laboratory conditions, reducing wave energy by up to 42%. And that capacity increases as the reef grows. The structure gets stronger every season, not weaker. Rutgers. University researchers, publishing findings in 2026, confirmed that living reef coastal defense systems reduce wave power significantly and become more effective over time as biological growth continues. The reef functions as a breakwater that repairs and upgrades itself for free. Traditional shoreline armoring costs hundreds of thousands to millions of dollars per mile to install and demands ongoing maintenance to stay functional. The Cedar Key reefs delivered comparable or superior protection at a fraction of that cost and required no maintenance at all. The biological system grew increasingly effective while the engineering systems were degrading. Coastal engineers who had dismissed oyster restoration as a fringe conservation project suddenly found themselves without a strong counterargument. By the early 2020s, the Cedar Key reefs had done something no conventional artificial reef in the region had managed. They had grown substantially beyond their original footprint without any further human input. The oldest sites had roughly doubled in total area since the initial deposits. No additional shells were needed. The reef expanded because oysters kept settling, growing, dying, and leaving shells that attracted the next generation. The reef was engineering its own expansion exactly the way natural reefs had built themselves for thousands of years before they were destroyed. The structural complexity had transformed. The initial deposits were crude mounds of loose calcium. What existed by the 2020s was architecturally elaborate. Vertical profiles, gaps between oyster clusters, overhangs, interlocking surfaces, creating dozens of distinct microhabitats within a single reef system. Crabs occupied the low crevices. Octopuses claimed the deeper overhangs as dens. Juvenile fish hid in the mid-level gaps. Sea turtles foraged across the surfaces. Dolphins hunted methodically along the reef edges, working the dense fish concentrations the way a predator works any reliable food source. Then researchers found something they had not been looking for at all. Dense oyster reefs lock organic carbon into their shells and into the surrounding sediments. As oysters grow their calcium carbonate shells, they sequester carbon that would otherwise contribute to ocean acidification and atmospheric warming. Studies were now finding meaningful carbon storage happening at the restored reef sites, a climate benefit that had appeared in the data without anyone designing for it. Oyster restoration began appearing in climate adaptation strategies, not only for habitat recovery and coastal defense, but for carbon management. A pile of restaurant scraps was now part of the conversation about how to address one of the largest problems the planet faces: Biodiversity readings at the mature sites were approaching levels recorded on pristine natural limestone reefs, the gold standard, the kind of structure nature takes untold years to build on its own. The gap between a restored reef built from discarded shells and the best natural reef in the region had narrowed to something researchers had barely dared to project. There's a concept that coastal scientists have increasingly started organizing their work around, and the Florida Oyster Program gave it its clearest proof of concept. It is called circular environmental design. The idea is that materials previously written off as waste, oyster shells, coral fragments, limestone rubble, can be deliberately repurposed as functional ecological infrastructure. Not as a feel-good gesture, not as a marginally better alternative to landfill disposal, as a precision design strategy with measurable, documented, improving returns. The Florida program did not just restore a reef, it demonstrated a philosophy, and that philosophy is now spreading. Australia has its own reef-building programs applying the same principles. Canada and European nations are studying the Florida model, looking for nature-based answers to erosion and water quality problems they have spent decades trying to solve with concrete and steel. International engineering teams that once defaulted to hard infrastructure as the obvious answer to shoreline erosion are now asking whether biology can do the job better, cheaper, and more permanently. The answer coming back from the data is yes. A restored oyster reef matched against a seawall is not a comparison between an ecological option and an engineering option. It is a comparison between a system that grows more effective every year and a system that begins failing on day one. It is a comparison between something that costs nothing to maintain and something that costs a fortune. It is a comparison between something that repairs itself after a storm and something that a storm damages. On every axis of that comparison, the biology wins. What makes the Cedar Key story genuinely extraordinary, what separates it from a remarkable environmental success story and puts it in a different category, is the trajectory. The initial deposits were a human intervention. Scientists chose the locations, barges carried the shells, people made decisions about where to put them, but by the time the reefs had been growing for a decade, the human role was essentially over. The reefs were self-sustaining, self-expanding, self-repairing. Each oyster that lived and died added substrate for the next generation. Each generation stretched the reef's footprint. Each expansion built more habitat, filtered more water, protected more shoreline, and supported more species. Every part of the system was strengthening every other part. The intervention had ended. The ecosystem had not. It was running on its own biological momentum, and the data suggested it would keep running for decades, possibly centuries. The shell deposits of 2007 had seeded a cycle that was now perpetuating itself without any help from the people who started it. They could walk away, and largely had, and the reefs would keep growing. That is the outcome restoration science rarely claims with confidence, because the field has enough examples of interventions that looked promising and eventually stalled. A genuine self-sustaining ecological recovery, one that does not require ongoing inputs, does not plateau, and does not rely on continued human management, is the holy grail of conservation work. It is the thing programs promise and rarely fully deliver. Florida delivered it. From discarded shells, from restaurant waste, from the material critics called ocean dumping, from something that everyone expected to fail and that the scientists running it privately hoped would merely show a few biological signs. Instead, it grew. It filtered. It defended the coast from a Category 4 hurricane. It pulled dolphins and sea turtles back into waters they had abandoned. It replicated itself generation by generation on the Gulf seafloor. And it inspired a model that is now being applied in New York Harbor and Bangladesh and along coastlines that have never seen a Florida oyster in their lives. 500,000 tons of what was going to a landfill poured into the Gulf of Mexico. And look what formed.